Okay, section 5.4. Here we have theorem 5.4.3. I think it's 3, yes. And so it says, hey, if f of z is a non-constant polynomial, so it's at least degree 1 or higher. Okay, polynomial with real coefficients. Then it can be factored. As a product of real linear factors and real quadratic factors. Real linear and real quadratic factors. So that is a pretty cool thing, in that if I have any size polynomial, polynomial with degree 100, I know that I eventually, if I worked hard enough at it, could factor it into all linear and quadratic factors. Okay, and so the way they go about this proof is they say, okay, so f of z has r real roots. Now r could be 0, but r real roots, and 2s, because we already know they come in pairs, non-real roots. Okay, and so the real roots we'll call z1, z2, z r. And then the non-real roots, again, they come in pairs, and so the way they're numbering them are zr plus 1, zr plus 2, r plus 1 conjugate. And they keep going until they get to zr plus s and zr plus s conjugate. Okay, so there are all your roots, and we know it has all those roots because of the Gauss factorization from 5.2, and so we can write the factorization if an is the coefficient on the highest degree term. We've got an and z minus z1 up to z minus zr, so there are all our real roots, and then times z minus zr plus 1, z minus z r plus 1 conjugate, and dot 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 up to the last one's z minus zr plus s. Oops, not conjugate yet. Well, z minus zr plus s. So I'll put the conjugate there and erase the other one. Okay. So I can write it that way. Well, so here are all the real terms, right? These first ones, so they're the linear terms. And then after that, then I do my complex conjugate pairs, and if we take any one of these, right, and we look at what that is, so I would have, and they change to a subscript of j for any of these r plus somethings. They say, okay, I've got z minus zj, and I'm going to put those together, so times z minus zj conjugate. Well, that's z squared, and then I get a minus zj z and a minus zj conjugate z, and I'll get a plus zj z j conjugate. Well, so there's z squared that has a real coefficient of 1, then minus, and I have this zj plus zj conjugate, and so let me write that as 2 times zj plus zj conjugate over 2, like that, and then plus our zj n times zj conjugate. Now, so this is just the real part of z. So this is equal to z squared, which has a real coefficient, minus 2 times the real part of zj. Oh, I forgot my z in here somewhere, times z, then times z. And then plus, this is our, the x squared plus y squared for that particular zj. And so here our coefficient is 1, that's real. Here our coefficient is minus 2 times the real part of zj, that's real. And then here we get the squares, the sum of the squares of 2 real numbers, so that's real. So this is indeed a quadratic with real coefficients. And so there we go. That is our factorization. Okay, and so then they mention their example 5.4.2, and they factor z to the 4th plus 1. So they say, okay, they do a preliminary factorization. They do a substitution and factor this. If I think of this as w squared plus 1, that's the same thing as w squared equals negative 1, and so we would have w is equal to plus or minus I. So those are the roots, and so what that means is this is, we can factor the w squared plus 1 into w minus I times w plus I, but w was just z squared, so w is z squared. So then that gives us z squared minus I times z squared plus I. Okay, so we have that, and then they just say it's easily verified, right? We've got a formula for it, and so forth, but they say it's easily verified then that for this one here, we would get z is equal to plus or minus 1 plus I over the square root of 2. And then for this one, we would get z is equal to plus or minus 1 minus I over the square root of 2. And so you see, as we look at that, if you think back to our geometry thing where we had these pieces like this, well, so if I start with, say, this first one, here is z equals 1 plus I over the square root of 2. Then from over here, I've got z conjugate is equal to 1 minus I over the square root of 2. Negative z is equal up here to this minus 1 plus I over the square root of 2. So there was the negative z. And then finally, negative z conjugate, and that would have been the negative of 1 minus I over the square root of 2. So there are those 4 points we looked at earlier in section, I think, 5.3. Okay, so that's our theorem 5.4.3 and kind of an example to go with it there.